So what is the other characteristic?
-2.
Maybe -1.
Let's make the toes like this. So this is the toes.
Maybe with the vertex.
And we make 4.
So now it has 2 faces. Now
It depends. Because
yes, 1 face. Yeah.
this face is not a disk. This part is not a disk.
Yeah.
So we cannot use that in the formula. We need always disk. So how we make that a disk? We add, for instance, the graph is disk. One vertex, because this vertex is the same. This vertex is the same vertex. And the edges, so we have B, these are the same. This is A, This is A and B. But we cannot say that this is a face because it's not a disk. So how we make a disk? We add some vertex here, W, and we attach one edge more. C. Now this is the remaining face is a disk because if we cut, this is a disk. So this is also an edge.
Nice.
So how many vertices? So vertices minus edges plus faces. So vertices, how many we have?
5.
Maybe it's in
2
every
words.
one, eh? Two words.
The 2 words. So
Because this is
same as
the same. When we do this face, it's the same. It's 2 vertices minus edges.
3.
4.
Or we have A, B, C, and D. And one face. So this is
minus
-2 plus 1 minus 2. And we can use the formula. So what is the genus? So the genus should be 1. So we use the formula. For surface with boundary components. So it's 2 minus 2g minus d. So we find here -1 plus 2 minus 2g. And we have one boundary component. This is the boundary component. -1. So the genus is 1. Any question or comment? Yes?
Please explain about boundary, like here you say that this is a boundary, and in case of obvious strip you said that there is just one boundary, and then in the second case you discussed that there are 2 boundaries. Can you please explain it?
Because I didn't give explicit definition of boundary. This is the cylinder. So every point that we take in the cylinder, if we take a neighborhood, it's like a disk, R2. It's an open disk. But what happens if I take a point here? How is the boundary? How is a neighborhood? Like half disk.
Yes.
This kind of point is what we call boundary. Here we have 2 boundaries, 2 boundary components. And in the negative band, we only have 1. Because we start to correlate the boundary. This is boundary. This is because the drawing is not good, but the boundary continues here. And here, any other, for
How
example,
is the boundary, that's a donut, right, hollow inside, how is the boundary one? What about the other side? How are they connected?
now this is only, this is like, what's the name? Tire, and we make a true. There are only one, we don't make it, we don't cross the whole tire. Only one punch.
Okay, it's from the top. Okay, got it.
Only
It was
one.
hollow inside.
No.
Okay.
It's, so for instance, in these curves, like outside, like the material is green, so this is green. But this green is the green that of the other behind. So maybe better drawing is like, so there are other ways to draw this. I can draw this like this. So if I open the hole, I open, it becomes this space. But I can continue to open. I can open more. This is isotopic. It's not only homomorphic, but this is isotopic. This is also this. It's the same object. So we open the hole more and more. So if you see, if I start to plot this, make it bigger, so maybe there is an intermediate step. Intermediate step is this. So if I open the hole, only this, and then I continue opening until this. So all are the same space, homeomorphic space. In fact, they are isotopic. All this can be done in three-dimensional space. So you can play with that with some material. I will draw other one, which is the same. It's homeomorphic, but not isotopic. So this space. So the space is made like I take one disk, I take a second disk, and then I will glue the two disks by using three disks. So one disk. So we are going to glue a disk here, but not in this way. What we do is that we twist. So the whole picture is still a disk, because I can twist and it's a disk. And I will do other one here. Now it's not a disk anymore. And I will do other one. So this is a surface. How many boundary components there are? So I start to color the boundary. So all this is boundary, boundary, boundary.
Here.
Only one boundary component.
Yes.
And then we can try to compute the genus of this surface. So you compute the Euler characteristic of the surface. And you will find that it's the same number.
Minus 1.
Minus 1. This surface is the same as this one. They are the same. That is why I say this drawing I don't like because we think in the genus of this whole, but this is also genus 1. This is genus 1. So they are homeomorphic surfaces, but they are not isotopic. So these are X and Y. So X and Y. Homeomorphic. But not isotopic. So the Euler characteristic for surfaces is a complete invariant. So we compute Euler characteristic and the number of boundary components, we know which surface is it. So here we have one boundary component, we compute the Euler characteristic. So V equals 1, Euler characteristic of equal minus 1, which implies that the genus is 1. So this surface should be that. This is complete invariant surface. This number, this is very beautiful theorem. Like the topology of surfaces is natural numbers. It's the same as natural numbers. Two couple of numbers. Genus and boundary. Any question, comment? So this exercise, compute this number.
Sir, boundary number should be same for every shape. Boundary component should be same. If the two things are
So the boundary here is, I will do the same code. The boundary is this one. Here the boundary is the boundary there is 1, here it is. So
If it is isotropic, then the boundaries will be same throughout the structures.
yeah, these three, so these three are isotopic. These 4, 1, 2, 3, 4, these are isotopic. But this one, these are not isotopic. And the reason is that the boundary here is always like this. The boundary here is complicated. This no trivial. This is the boundary. That is the reason why they are not isotopic, because this knot and this knot are not. Any question or comment?
Is there any relation between isotopic and boundaries? If it is isotopic, will the boundaries be of same numbers, or is there anything else?
Yes, yes. So if two spaces or manifolds or any x and y, if they are isotopic, then they are homeomorphic, and therefore the number of boundary components is the same. But moreover, if they are isotopic, then the boundaries are isotopic. So this relation of isotope to be isotopic goes to boundary, like homeomorphism also. Same. Any other question or comment?
If boundaries are same doesn't mean it is isotopic, just like this example.
Yes. And so topology started like this. So Euler and Poincare, so they were thinking of topology like this before the definition I wrote at the beginning. So that definition came later, many years later, almost 30 years later. But they were doing all this and more, many more. So when we study general topology, I will teach that course this semester at university, and I don't know how to motivate the definition, because that definition is the final result of many years of work. But when we start to study, we start by that definition, and I think it's very bad for brain, because we cannot find that definition from nothing. Any question or comment? Does everyone know how to compute this number? How to get -1 from this? Everyone knows how to do it.
Say no or say yes. Okay, if you don't know, then say no. If you know, then say
If
yes.
you don't know, we can do it.
You can do it again.
Because the purpose is learning. So
Say something. Okay, talk.
do you want we do it now?
Yeah.
So let's do it.
Simple, right?
So we have this space. You can make this space with 2 pieces of paper. 2 pieces of paper. The usual drawing of this is like a cake. So with this, we put 3 bands. So you can do this with paper to understand the space better. And let's compute. So we need to make some graph on this space, such that when we cut, we obtain disk. So the best graph is, let's take this vertex, 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 vertex. And here, 2. All of that are vertices. So how many? change the edges. So this edge components. So vertices how many? 12.
12 minus
18.
Yes.
And how many faces?
1, 2, 3, 4, 5, 6, 7, 8, 9.
5.
Five.
So this one here, and 1, 2,
2, 3, okay.
What about the outside?
Outside.
No, there is no outside here. Like in the torus, there are no outside. So when we do in the plane, there is an outside, but it's because we are thinking that the drawing is in a sphere. So the outside is inside. So which number is this? Minus. So this complicated space is just the same.
I don't know if it's a whole.
So it is. So it has genus 1, but here we cannot see the genus, like the genus 1. Any question or comment? So I make an exercise for you. So I draw some surface, I draw two surface. With one boundary component. But I want that the boundary is not the circle. It's not trivial circle. So it should be something like this, but this is genus 1, so we want genus 2. Any question or comment?
For the formula, you have to put orientable, right?
Ah, yes. This is orientable surface. This is orientable surface. This surface we can color with 2 colors. This is orientable surface.
Can you please explain about orientable and non-orientable surfaces? Like, is there any mathematical definition for that?
Yes, but it's not easy. So intuitive definition is we start to color and we have 2 faces. For instance, in the sphere. We can color outside with red, and if someone is inside with blue.
Yes.
And there is no problem, the colors never mix. This one same. I start to color here green, and I twist. So this is not green.
Yes.
This is maybe orange. Orange. Orange.
And that is green.
This is green. And below, this below is orange.
Yes.
And this below is green. So this is orientable.
Okay.
So that is an intuitive definition of orientability. But mathematically it's more difficult to define. One way is that we can put normal vector, non-trivial normal vector, in a continuous way everywhere. So here the normal vector comes back, but we can do it that. But that is difficult definition because to define normal vector field we need more better definition of this object. And there are topological definition by using homology. So all definitions of orientability are not easy. This one is intuitive definition, and it's enough for us.